All right, today we're going to be looking at section 5.4, modeling and optimization. So here's some key vocabulary terms to keep in mind as we go forward in this section. Optimization is a process for finding a maximum or minimum value that fits within constraints of a situation. A constraint is a condition or limitation in a problem that must be met for any potential solution to be valid. An extreme value, which we've already had this vocabulary term before, but just to reiterate it, it's a maximum or minimum value for a function that will be a potential solution to an optimization problem, though, in this context. All right, so here's some general strategies for solving optimization problems. First, you want to make sure you read the problem carefully. Wording is very important. Reread the problem. I encourage you to always read the problem and reread it, sometimes multiple times, especially when it just depends on the problem, but you really have to read the problem very carefully. Identify key information in the problem. You want to pick that key information out and you want to list that out somewhere where you have that in the problem, or underline it perhaps as you're going along and reading it. You want to draw a picture. A lot of these problems are going to be geometry in nature, so a picture is definitely necessary for you to be able to make sense of the problem and persevere in solving it. You want to introduce and define a variable or variables depending on what we're looking at. You want to write an equation using the variable or variables whose extreme value gives the information desired. And finally, or well, not finally, because there's actually a couple more strategies on the next slide, but you want to graph the function. You want to find the domain that makes sense in the problem and fits the constraints that were given in the problem. Okay, basically when we're looking at constraints, I'll say this also about constraints, you're going to be thinking about certain values. If we're doing these in geometry and nature, we're talking about a real world situation. It's not practical to think of lengths being negative, for instance, or heights being negative, or whatever geometric dimension that we're talking about. Sometimes negative values are not going to be accepted in the domain. So therefore, your function that you write is going to have a specific domain that's going to be based off of those constraints. That's kind of what we're thinking about there with that. All right, so here's some more strategies you want to find and steps to solving these problems. These are strategies and steps, really. But you want to find the critical points and the endpoints. Those will be determined from, the endpoints will be determined from your domain. You want to perform any necessary tests to determine what kind of extrema occur at these points. Okay, because you want to make sure it is a maximum or a minimum depending on what you're looking for. And lastly, and most importantly, interpret the solution in the context of the problem and make sure it does make sense. This is especially important on the AP test with FRQs. These problems do tend to be free response questions quite often, but not to say there aren't multiple choice questions also that are these problems. But you have to interpret the solution in context when you're doing a free response question. If you don't do that, you're going to receive a low score on that question, even if you get the right answer. It's got to be in context. All right, so we're going to look at an example here. We're going to kind of utilize some of our strategies going forward here to help us be able to do this problem. So we want to find two numbers whose sum is 20 and whose product is as large as possible. Okay, so we want to introduce a variable. We can say x is our first number. And you can have another variable if you want to. You can say that y is the second number. But a lot of times we're going to be looking to try to get everything in terms of one variable, because we only want to do single variable calculus here. We don't want to do multivariable. So we may have to rewrite y in terms of x, but we can do that using something we know here. we know that their sum is 20. So if their sum is 20, x plus y has to equal 20. So therefore, y would equal 20 minus x. So that second number is also can be written as 20 minus x. We need to identify what we're trying to do here. Read the problem very carefully. Find two numbers whose sum is 20 and whose product is as large as possible. So are we trying to maximize or minimize? You should see the word as large as possible and think, oh, that signals that I'm trying to max something. I'm trying to max this out. And what I'm maxing out the product. So our function, we'll call it P of x, product function, we're going to multiply our numbers together, x and 20 minus x. Now I used x and 20 minus x because I want it all in one variable. So that is our product function that we're trying to maximize. So we'll take that, we'll simplify that out, we'll get 20x minus x squared. And that's our function. So we want to find the maximum, so we'll do just like what we did in this last unit. We'll take and do an appropriate test. We'll first take and find our derivative. The derivative of this would be 20 minus 2x. We want points where the derivative, critical points, we want points where the derivative fails to exist or the derivative equals 0. Now, let's think about this for a moment here. We really aren't given anything as far as constraints. We always want to go back and make sure there weren't any constraints on this. It doesn't really tell me anywhere in here that I want the numbers to be positive or negative or anything like that. This is not really a geometry application of this, but I always like to start with one maybe that's not as geometric in nature and then work our way up. So for this one, we're actually just going to go ahead. We don't have any constraints on this. So this function right here, this is a linear function. That's going to be defined everywhere. So I don't have points where the derivative fails to exist. So I'm going to set that equal to 0. 20 minus 2x equal to 0. And I'm going to solve that. I get 2x equals 20. If I move 2x over by adding it. And then I divide by 2 and I get x is equal to 10. Okay, you can so you need to perform a test to make sure that this is a maximum, to make sure we do find a maximum at 10. You can do a first derivative test or you can do a second derivative test. I'm personally a bit fond of the second derivative test. If I take the second derivative, p double prime of x, if I do the derivative of 20 minus 2x, I get negative 2. That's negative 2, that means it's concave down everywhere. Because negative 2 is always going to be negative, so it's concave down everywhere. So if that's concave down, then therefore x equals 10 is a maximum. Because if it's concave down, it's curving down, you're going to have a maximum. So we do this in context. The two numbers we desire in this situation are the two numbers that we desire in this situation are 10, and if they're going to add up to 20, the other number will also be 10. So to maximize that product, I need to have 10 times 10. Let's think about that for a minute just to see if it makes sense. Well, 10 times 10 is 100. So that product, the biggest product I can get is 100. What if I decreased one number, increased the other number? They have to add up to 20. So what if I did 9 and 11? 9 times 11 is 99. And if I do 8 times 12, 8 times 12 gives me right off the top of my head, I'm having a moment here. 96, okay? You can see that the product is getting smaller as I decrease one number and increase the other one. So the biggest product I can get is if the two numbers basically are the same in this situation, 10 and 10, okay? Now, sometimes the problem, instead of saying find the two values or find the two numbers, it may say, hey, find the maximum product. Then you would have to say the answer would be 100. The maximum product occurs when the two numbers are 10 and 10 and the maximum product is 100. You have to read the question, make sure that you've answered the question, because slight changing of wording can totally change the meaning of the problem. Okay? So let me erase that and we'll go to the next example we're going to look at. All right, a rectangle is inscribed under an arc of a sine curve. What is the largest area that the rectangle can have, and what are the dimensions given that area? Okay, well, let's draw a picture of that. Let's draw a sine curve. We know sine goes through the origin. And the sine curve would keep going down below the origin past that point. It would go down and do another loop and then come back up and then start over again. But we want to put our rectangle underneath this sine curve. So we're going to draw a rectangle underneath this sine curve, and we're trying to figure out what are the dimensions that will maximize this area of this rectangle. So we know that the rectangle has vertices here and here. We'll call these point P and point Q. We know that naturally, we know that the sine curve intersects the x-axis at 0, and the next place it does it is at pi. That comes from trig. That's the next place that sine is going to be 0, is at pi. So we need to introduce some variables here. So we don't know what the x-coordinate of point P is, so we'll just call it x for right now. Whatever that x value is, though, the y value right there is going to be sine of that, because it's a sine curve. We're looking at whatever sine is right there at that x value. So point P has coordinates x, comma sine x. Okay, the y coordinate would be whatever the sine value is there at x, because I'm defining x to be the x coordinate of P. Now, because of the way that I'm drawing this, we're obviously going to want the distance from 0 to this point to be the same as the distance from this point right here to pi. So whatever this right here is going to be, when we're looking at this distance right here, this is going to be whatever pi, this distance is going to be the same as that distance. So it's going to be another x. So the coordinate of this point right here, point Q, is going to have a coordinate of pi minus x. Because I'm going to take pi and I'm going to subtract x off to get right here where this point's at. That's going to be the x coordinate. Now, the y-coordinate there, though, the y-coordinate, yes, it could be sine of that, but actually, because the way sine works, we know also geometry-wise that this side is going to be equivalent to this side. So if that side has a y-coordinate of, the y-coordinate being the side of the rectangle right there, if that's sine of x, this is also sine of x. And the reason why that works is because sine is positive in quadrants 1 and 2, and as we go between 0 and pi, there's going to be two values where sine is going to be the same value. Two particular x values, two particular input values, you could say, where sine is going to be the same. You have sine being for instance, you have sine being 1/2 at pi over 6 or 30 degrees, and you also have that at 5 pi over 6 or 150 degrees. If you think about your circle, the unit circle. So the way that sine works, that would be the point Q. Okay, now we're trying to maximize the area. We know the area of a rectangle is length times width. Okay, we know the area of a rectangle is length times width. So if I'm trying to maximize area, I need to write length and width in terms of this. Well, the length of this rectangle, that'd be this distance right here. If this is x and this right here is x, then this distance right here is going to be pi minus 2x. So the length is pi minus 2x because I'm going to subtract off the x on either end there. So pi minus 2x is my length, and my width is sine of x. Okay, that's the height, or whatever, you can even say height. You can do base times height instead of length times width, whatever, of the rectangle. So that's the width of that rectangle is sine of x, because that's the y coordinate at both of these points. So that side is sine of x. So my rectangle has dimensions pi minus 2x and sine x. So our area function that we're trying to, the area function that we're going to write here is going to be these things multiplied together. I'm going to have pi minus 2x times sine x. Okay. Let's find the derivative. Let's take the derivative of that function. Let's do the product rule. First times the derivative of the second. Derivative of sine is cosine. Plus the second times the derivative of the first. Derivative of pi minus 2x. Pi is a constant, so its derivative 0. Derivative of negative 2x is a negative 2. So I basically get pi minus 2x times cosine x minus 2 sine x. We cannot set that equal to 0 and solve it algebraically. There's not a way we can solve that algebraically. So we'll do it graphically. Set it in the calculator and look to see where it equals 0. Okay? What you'll do to do that, you'll want to type that in the calculator. In a function, you want to type that function, pi minus 2x times cosine of x minus 2 sine x. And make sure you are in radian mode as well, real quick. And then you're going to hit graph. Now, we know that our constraints here, we know that x has to be somewhere in between. It's bigger than 0, but it's less than pi. So we know that we're in between 0 and pi there for our constraints, because we know that we have to be under one arc of the sine curve. So we can't be, we could be very close to pi over here. We get a very thin rectangle. We know that probably doesn't make sense though in the problem though, because we're going to maximize the area. But we got to be as close as possible. So we don't want to go in too crazy here. But once you have the function graphed, that's what the function looks like. It's kind of crazy. But what we want to do is we want to find zeros, and we're probably looking for these right here close to 0, just positive, but close to 0 right there. So we'll go to second calc, the second trace. You're going to go to 0. You're going to do a left bound of 0 and a right bound of, I know that it's going to be somewhere between 0 and even, I could probably say even pi over 2 for that matter. Why pi over 2? Because that's going to be the halfway point right here. That's going to be the highest point of my sine curve. So You could do a left bound of 0, enter. You could do a right bound of pi divided by 2, enter, and enter again, and you get your first potential answer. A prime of x equals 0 at x is approximately 0.7105. I'm just going to round to 4 decimal places. We got to do another one because there's one more that's really close there. Do a left bound now of pi divided by 2 and do a right bound of pi. And you get your second answer of 2.43 1. Okay, so those are our potential minimums and maximums. We have to test to see whether those are the actual minimums or maximums, though. All right, so to do that, to test these, we can try to do a sign chart real quick. We've already got our derivative in there, so we want to pick some values. These are our two values here, 0.71 and 2.43. We obviously want to stay within our bounds too, so we want to pick something less than pi. So 3 is a good choice for for a test point past 2.43 because that's less than pi. 1 would be a good choice in between. And we don't want to pick 0 really because that's our end point down there. So we'll just pick 0.1. We're going to let the table do the work for us anyway. So 0.1 at 1 and at 3. What we get is positive, negative, positive. So based on this, I did a first derivative test here. We're increasing, then decreasing, then increasing. So I'm increasing, I'm decreasing, then I'm increasing again. If I'm increasing and then decreasing, this is a maximum. Okay, because you're going up, then you're going down. So that had to be a maximum. Now I'm going down, whoops, that's a negative. Now I'm going down, and then I'm going to go back up. This is a minimum. So we don't want to use that value because that'll be the minimum. We want to maximize the area, so we're going to use 0.71. Okay, so our dimensions, we would take that 0.71, we would plug it back in here to get our length and our width. Okay. So we plug that back in, we have pi minus 2 times 0.7, it's 7105. Okay. We get approximately 1.7206, and then we also do sine of 0.7105. Because we're wanting to get those dimensions, our length and our width. All I'm doing is plugging the x value in for the length and the width. When I do that, I get the width to be 0.6522, And then I also want the area, that's the maximum area, so I'm gonna multiply length times width. So that's 1.7206 times 0.6522. And that gives me an area of approximately 1.1222. That would be square units. Or units squared. You can write it units squared. So to write this answer in context up here, I'll do it up here because I'm out of space down here. To write this in context, the rectangle with the largest area under one arc of a sine curve has dimensions 1.7206 units by, you can use a big X for by, 0.6522 units. And the maximum area is 1.1222 square units, or units squared. That would be that answer in context. All right, I want to do one more example, and then we'll be done with this part of the lesson. Although there's a little bit more, we'll probably do optimization for a couple days here with this. This definitely takes some getting used to. All right, an open top box is to be made by cutting congruent squares of side length X from the corners of a 20 by 25 inch sheet of tin and bending up the sides. How large should the squares be to make the box hold as much as possible? And what is the maximum volume? Okay, so we're kind of going three-dimensional here with this. All right, so we definitely need a picture. We need a picture of a piece of tin. Okay, so we want 20 by 25 inch. So it's a rectangle. All right, we've got our rectangle here, and we want to take this rectangle and we're wanting to cut, we want to cut squares out of the corners. Congruent squares out of the corners, and they're going to have side length X. What we do when we do that, once we remove those, you think about it, once we remove these, okay, I'm going to make these squares now dashed. What we're going to be able to do is take now and we're going to be able to fold up the sides. Fold up these sides right here. So this right here now be, this rectangle in the center here will now be the bottom of the box. I'm terrible at drawing, sorry. Okay. That will now be the bottom of the box. I'm going to fold up these sides here. To where now I'm going to have a box. Okay. We know that the original sheet of 10 was 20 by 25. Okay. We're trying to maximize the volume. We want to hold as much as possible. If it's going to hold as much as possible, we're trying to maximize the volume. Okay, so we're wanting to try to maximize the volume here, so we definitely need a function for the volume. We've already introduced a variable here. We made the side length x. The problem actually had that for us. That variable x already introduced in there for us. So we need to write a formula for the volume of the box. Well, the volume formula, I'm going to write it up here at the top. Volume for a rectangle or prism like that is length times width times height. Okay? That's my volume formula. I need to write length times width and width, and height though in terms of x. Okay, well if we're folding up these sides here, the height of the box is going to be x. So h is equal to x. I need length and width in terms of x. Okay, so the original length of the 10 was 20, right? 20 by 25, so the original length was 20, but I've removed some here because I've cut squares out that are x by x. So I've removed x from this side, but I've also removed x from that side. So I really have taken 20 minus 2x because I've removed x from either corner there. So the length is 20 minus 2x. And likewise, the width was originally 25, but now it's 25 minus 2x because I've taken x off of either end of that as well. So that allows us to write our volume formula. Volume, V of x, is going to equal x times 20 minus 2x times 25 minus 2x. I know you do not want to use the extended product rule to derive that, so let's do the algebra real quick. Let's distribute and simplify. That's going to be 20x minus 2x when I distribute that x in that first one. Still got it times 25 minus 2x. I'm sorry, that's 20x minus 2x squared. My bad. Now I'm going to double distribute here. 20x times 25